Richard Feynman came up with a way of representing how particles interact, and also how to represent the forces using exchange particles responsible for the interaction. So for the electromagnetic force, the exchange particle is a virtual photon. When two protons move towards each other, they experience a repulsive force, and the electromagnetic force is responsible for this. Feynman's idea is that time runs upwards in the diagram. Okay, so you've got two protons moving together. They exchange a virtual photon, which we represent with a gamma symbol, and then the two protons repel. The exchange particle responsible for the weak nuclear force, the weak nuclear force being the force that occurs during beta decay, are W bosons. These are different to photons, virtual photons, because they have non-zero rest mass, i.e. they have mass. They've got a very short range, approximately 0.001 femtometers, and they are charged. Sometimes you're asked to calculate the lifetime of particles, and if you know the range, which is effectively the distance, and the fact that they can't travel as fast than the speed of light, then you can work out their maximum lifetime using time equals distance over speed, and speed being the speed of light. The interactions that I'm about to show you for the weak nuclear force are quite rare. Neutrinos, which are these here, that's a neutrino and an antineutrino, hardly interact with anything. And these two interactions, the neutron-neutrino interaction, the proton-antineutrino interaction, as I said, are quite rare. So what goes on here? Well, for the first one, the neutron-neutrino interaction, we have a W- boson, which is the exchange particle for the weak force. And then what happens is you get your neutron going into a proton and your neutrino going into a beta minus. What's a beta minus? Well, of course, it's an electron. And if you look at the charge below the diagram, you've got a neutron and neutrino, which is neutral. And above, you've got a proton, which is positively charged, and an electron, which is negatively charged. The charge is conserved. On the right-hand side, we've got proton and antineutrino interaction. This time, we have a W plus boson, representing is the exchange particle of the weak nuclear force, and this time the proton turns into a neutron and the antineutrino results in a positron. Okay, so again, if you look at the charge below is positive and the charge above is also positive. The more common example of the weak force is beta decay. And as we've already looked at the neutron in one of the neutrons in the nucleus turns into a proton. And as this happens, we also get a W- boson decaying into our beta minus, which is our electron coming from the nucleus. And also, we've talked about the fact that we also need an antineutrino to conserve the energy. For beta plus decay, i.e. positron decay, we have a W plus boson, and this decays into a positron and a neutrino. Again, time is running upwards along the screen here, and that proton turns into a neutron in the nucleus. Again, looking at charge, the charge below will equal the total charge above. And the last Feynman diagram I'm going to show you is electron capture. Sometimes in a proton-rich nucleus, a proton turns into a neutron as a result of interacting with one of the electrons in the inner shell of the atom. Okay, and this happens as a result of the W plus boson, and our proton again turns into a neutron, and the captured electron from the inner electron shell goes into a neutrino. Charge below, we've got positive and a minus, makes it neutral, and above, again, we've got neutron and neutrino, makes the charge neutral. There are many more Feynman diagrams, but these are the main ones you're expected to recall and be able to draw.